All right, for sake of time, we'll go ahead and get started. I might repeat myself maybe towards the end of the first few slides here just to let everybody know. Thanks for joining us. We're going to be going through, how to really back up your home here, whether that's, through the right methods or the wrong methods. We're going to kind of talk about what's the best solution and how MorningStar products work and SimpliPhi products work, and really how we can meld the two together to build some really resilient systems for customers. Just some housekeeping stuff. After this presentation, we'll be sending out follow-up. We'll be sure to add the PDF of the slides so you can have that. You can respond to that follow-up with any follow-up questions, inquiries, from MorningStar or SimpliPhi, and we'll be sure to get back to you and help you out if you have any sales, technical stuff, whatever it may be. Happy to help. We are recording today as well. We'll be sure to pass that along once it's edited down. Probably won't go out with a PDF, but it will go out once we have it all cleaned up and ready to go. Just really quick, we do have some time carved out at the end. There's a lot of participants today, so I don't know if we'll be able to get through everyone's questions, but we do have a Q&A section here. You can actually type right into that Q&A. So any questions you have, just type them in there, and we'll be sure to get through as many as we can at the end and try to get any lingering questions after the fact. All right, so with that said, my name's Troy Daniels. I'm here on the left. I'm the Technical Service Manager. I work for SimpliPhi Power, and we also have Jake Sherry here, Application Engineer with MorningStar Corporation to present. So you'll hear me talk for a little bit, and then I'll hand it off to Jake, and I will be wrapping up at the end. Okay, so power outages. Why is this, in quotations, the new normal? Well, with infrastructure growing, things are only, as far as I can see, only going to get worse with power outages. We're going to see more power outages. We are seeing more power outages more frequently, and even planned power outages, which we'll get into here in a sec. So, just some headlines related to that. I think a lot of this is, these three headlines specifically are related to California. There's definitely a light shined on California right now. No pun intended there, but of power outages. And really, with the power outages that, PG&E, even with, planned power shutoffs, we're seeing backup power really is becoming a vital thing, especially for, if you're living in an area maybe that's prone to fires, maybe your household requires some sort of medical devices, things like that. It can definitely be a big thing and something to consider. So again, the power outages, this is what I was talking about, the planned power shutoffs, for those that do not know, where they're actually shutting off the power on purpose. And we're definitely seeing a demand and a growth of how to deal with those power outages, and really looking at battery backup as the solution. But the question really still lies is, what's the best way to handle these outages? What's the best way to expand on the solar system that's already in place? And what's the best way to add batteries and the best cost-efficient way as well? So the real question I'll pose here is, why can't grid-tied solar work on the rooftop? Or why can't grid-tied solar on the roof help in these power outage situations? And we're going to go into kind of what solutions do work. With that, I am going to go ahead and hand over the controls to Jake here. And Jake, you have the floor.
All right. Thanks, Troy. Can you hear me all right? Okay. Let's see. So just try to go forward here. Oh, I'm sorry, Troy. I think
that's okay. Let's try again here. Sorry, guys. Technical difficulty. We got it, though. 1 second. All right. Let's try one more time. All right. Go ahead and try to take the controls here. See if that works.
Do that. Says you are controlling SimpliPhi Power screen.
Perfect.
Right. There we go. All right. So now I'm good. So one of the misconceptions, for those, many of you probably already know this, but those less familiar with the solar world would be surprised to find out that traditional grid-tied solar systems involving just a solar array and a string inverter feeding your main AC panel and selling back the rest to the grid through a utility meter, that's not going to do anything for you when the grid is down. It's purely dependent on the grid's operation to harvest that solar power and actually do anything with it to offset your loads. So again, when it's operating fine and the utility is in normal operation, it's a simple, efficient, and very effective way to, incorporate solar. However, again, when you lose that connection to the utility during a power outage, that isolates everything, and everything has to shut down. Therefore, all of the solar real estate you have on your roof, lined with panels absorbing sunshine, is not going to be able to do anything for you because there's nowhere to put it. There's nowhere to push it back to. You can't push it back to the utility while people are working on the power lines to get things back up and running. That's a safety hazard. So it has to isolate itself and shut down. So in other words, you got a useless solar array in the event of a power outage. Of course, there are solutions. They come in different forms. One would be adding a generator, which is, again, fairly common. Generators have come a long way in, reliability, even consuming less fuel. They're certainly they're not very expensive, so that's a good thing. Batteries can be more expensive and traditionally are. However, they're loud, noisy. They, create pollution, CO2 emissions, and you have to maintain them. And, you have ongoing costs for maintenance and fuel. Talk about those in comparisons in just a little bit. Also, there are AC coupling. We'll talk about specifically what that means. AC coupled systems. You have DC coupled systems as an alternative in the traditional sense, where you're mostly using low voltage PV arrays, different than the voltages you typically find on most grid connected homes, where they're allowed to go up to 600 volts as the limit. Traditional DC coupling, as it stems from more use case in off-grid scenarios, we're traditionally using lower voltages, but there are higher voltage derivatives of DC coupling these days as well. So we'll talk about that. And then Morningstar's take on it, it's kind of a unique approach to provide backup to an existing grid-tied system through incorporation of a DC transfer switch, which we call direct DC transfer charging. So we'll highlight that solution in just a sec. So again, as I mentioned about the generators, these are really the top downsides to using generators. Again, doesn't really fit in line with the go green mentality of many people in our industry. So that in and of itself would, may turn some people away. But, again, not necessarily considering, if you're talking about pure off-grid systems and with, lithium batteries and expensive storage solutions to provide the full range of autonomy that your system needs, it can be hard to do that with batteries alone. So sometimes it may be good to incorporate a generator as a supplemental source of backup and not purely rely on one or the other. And that's what, we'll talk about coming up. So this chart is a little bit difficult to read, I think, in this type of a presentation, but I will say you should have the PDF handout of the slides you can take a look at after the presentation, look at it in more depth. But again, just to kind of cover a few topics, we're looking at DC coupling, AC coupling, and backup generator comparison here, and some of the constraints in terms of sizing and behavior that you need to be aware of for each one. The nice thing about the DC coupling with respect to the array is you're traditionally using a MPPT charge controller, being fed from the solar panels, and the MPPT allows for some amount of oversizing beyond what your batteries can store. So you can have, a much larger array to a smaller battery size ratio and still maximize the amount of time that you'll be able to achieve full production with respect to the amount of charging needed. And then also, again, that allows the battery bank itself to be smaller, whereas AC coupled systems, traditionally you end up with oversized battery banks, especially, when you're thinking about lead acid, only able to use, 50% of the battery bank. It's a lot of investment for half of it to just sit there. And it doesn't add any more runtime for you in terms of your load operation or any more autonomy. So those are things you just want to be aware of. And just the flexibility, with respect to the battery-based inverter sizing with DC coupling, you don't have to size it relative to the string inverter size because it's a completely different circuit, and it's purely dictated by the loads that you're running for critical backup. Anyway, those are just a few of the highlights, but feel free to look at this chart more in depth. We will cover some of this content coming up as well. So if we just take a look at AC coupling first and foremost, this is, has been a popular way to add storage to existing systems for a long time. It was really developed originally as sort of a workaround or patch fix. The brightest minds came up with this, and it certainly has some limitations. They've improved on some of them, in the more modern forms of AC coupling. So, reliability is a little bit better than it used to be, but there's still some shortcomings, and we'll talk about those. Mainly, you can see what I mean by a workaround solution. With AC coupling, you're going through a double conversion process, which in and of itself is inefficient if you don't need it. Again, what's happening here is you have your PV array feeding your string inverter. That's inverting DC to AC. And what you're actually doing is you're backfeeding the AC output of your battery-based backup inverter charger to make it, to fool it into thinking that the grid is present. And so the string inverter is allowed to push energy through the DC, through the AC output of the backup inverter charger and backfeed this AC to DC rectification stage to charge the battery bank, albeit fairly unregulated. A lot of times you just have a simple on-off capability through a relay controlling the DC output to the battery. And, on-off charging is certainly not as efficient or sophisticated as modern variations of PWM, charge control pulse width modulation. We'll talk about that as one of the technologies we incorporate into our charge controllers to maintain a much higher battery state of charge, which is what you want to do. A lot of times when you're backfeeding the energy from a string inverter back through the inverter charger, going through that additional AC to DC conversion, it's coming out here almost like a fire hose, and there's no way to dial back the current going into the battery bank unless you have some type of more sophisticated frequency shift modulation or, direct communication and control between the string inverter and inverter charger components. But again, all of that energy that's being produced by the array has to go somewhere, and it has to go into the battery bank. Now, when you're just all of a sudden shutting off that nozzle, just like shooting a fire hose into a bucket, you're not really going to have any good sense of awareness as to when that water level is getting close to the top. You're going to turn it off. It's either going to overflow or it's going to be, it's going to stabilize. And when the water subsides and reaches, a constant level, it's going to be at 80% full, which is not good for maintaining batteries for, prolonged lifespan. You want to get them to that 100% state of charge occasionally. And we'll show you why that DC coupling is a much more effective way of doing so. So again, with traditional DC coupling, this is what you have. And I mentioned before, you can do it with low voltage PV arrays. Again, more modern charge controller manufacturers, MorningStar included, have been drawn to doing this at higher voltage. So they can do it at up to 600 volts with our TriStar MPPT 600 volt charge controller, which you see pictured here. And again, what this does is, in this scenario, you have no string inverter. So really, traditional DC coupling is better, not from a retrofit perspective, but from a new system perspective. When you're installing the system new, you don't have any existing hardware. You're installing your PV array at the same time as all of your charge controllers and inverters and BOS components and everything, your whole electrical system. It goes in nice and easy, and there's a lot fewer components to worry about. And so in this sense, you can still have this in a traditional off-grid sense where you are not connected to the grid at all. Maybe you just have a generator as your supplemental AC charging source. Or you could be grid connected, and you could be sophisticated grid interoperability modes with some of the newer hybrid inverter chargers that you might find out there with, again, different operating modes to limit your cell back, zero export control. You can feed in, the rest of your power to the grid for net metering, or you can get, time of use and some of those other sophisticated operating modes. They can all be facilitated with forms of DC coupling, mostly dependent on your selection of inverter charger. And then what we'll talk about here is the proposition, or the solution that MorningStar proposes is a little bit of a unique derivation of traditional DC coupling. And so this would use our a variation of our 600 volt controller that comes equipped with a DC transfer switch, which is that black knob right there. What this allows us to do is we can, in some way, have our cake and eat it too. So from a retrofit standpoint, it becomes very cost effective to keep your string inverter. Your existing PV array is, wired to 600 volts max. You don't have to do anything. You don't have to change anything about your existing grid tied operation. You still have your PV array. It's feeding your string inverter, powering loads at the main AC panel, backfeeding the rest to the utility. And that's it. Now, by adding in our 600 volt charge controller equipped with the DC transfer switch, we can preserve that efficiency of the string inverter in just straight conversion, DC to AC, straight through to the main AC panel. And that is, again, you're looking at conversion efficiency for modern string inverters at 99.9% efficient. I mean, they're really high, 99.25, 99.5. They're really a step and above beyond the efficiency of battery-based systems in terms of selling to the grid at those higher voltages. So that's where, again, it's important to preserve that operation. But what we can do is, when we equip with the transfer switch, it's a double pole transfer switch, we can change it to the battery controller selection. So we just turn the knob vertically downward, and that closes this switch here, which allows the charge controller to use DC coupling to charge the battery bank. And the DC to DC conversion is very efficient as well, keeping everything on the DC side. You don't have to do that double conversion that's associated with the AC coupling method. So again, for this controller, I think it's 97.9% efficient charging from, up to a 600 volt array to your 48 volt battery bank. And then you have your separate battery-based inverter charger here. This does not need to be one of the more sophisticated varieties in terms of grid cell interoperability modes and certifications, et cetera, that may add unnecessary cost to the system. It can be just a pure and simple basic inverter charger. Many of them in today's world have a built-in automatic AC transfer switch. So again, as soon as the grid input source stops feeding, it's going to turn on the inverter instead. So it's going to then take the DC to AC out to your critical load subpanel. And while the grid is operational, again, you'll get the power produced from your array through the output of the string inverter to your main service panel. Again, some of that power will be relegated to charge the battery before, when the AC transfer switch is in the opposite position. So again, it's going to change based on your operating mode. The AC transfer switch does so automatically. When the grid is lost, you'll change over to inverter and pick up the critical loads, basically as a UPS, depending on how responsive the inverter charger is. And then also the charge controller, again, will allow, the automatic AC transfer switch will turn into inverter mode when grid is lost, so that you can take the power out to the critical loads. All right, so let's go on to the next slide here. We'll talk about more of the specific advantages. Let's see. So really what we're going for here is the low-cost entry point of this solution. You don't need to make any alterations to your existing grid-tied system. So from an installation standpoint, it's very easy to add on after the fact. You could have a grid-tied system operating fine for many years. All of a sudden, you start getting more of these outages, whether it's from storms or planned outages. You can add this in a very non-invasive way to your existing system. And again, it allows you to preserve the high efficiency operation of your string inverter. You don't want to just throw that away, because as I talked about before, with the traditional DC coupling, and you're using, just a single hybrid battery-based inverter charger that is taking care of the grid interoperability as well, in terms of pushing power back out, or some of those, more sophisticated interoperability requirements. They're doing so in converting from battery voltage out to your grid voltage. And that is a lot less efficient than taking the PV array straight through the string inverter and out to your utility. So again, in terms of selling, and every bit is important with regards to, the reimbursement structure or net metering. You want to preserve as much of that power going back to the grid as possible. And so having the higher efficiency operation of the string inverter is important there. The smaller battery banks you can accommodate without having to size that in tandem with your PV array. So that's really nice, is that the two can be independently sized. It's not a domino effect. If you change one thing, it's going to affect the size of every other component in the system. And again, having the ability through, the DC to DC control to tailor the maximum charge current for your specific battery so you don't exceed its maximum charge rate. That's, a positive advantage as well. So there's many things that you can see with this type of solution that will enhance the overall. It's going to get you a lower cost entry point relative to AC coupling, and it's going to maximize the efficiency of the operation and the reliability of your system overall. Your batteries are going to last longer because they're being treated better. So again, this is the direct DC transfer charging solution from MorningStar. It uses our TriStar MPPT 600 volt controller with the transfer switch. There are two versions available. One is just the controller as you see it here, has the built-in transfer switch. The other one comes with a pre-wired GFPD, which is nice as well for the ground fault protection requirements and safety for NEC. It represents a good value having all of that incorporated into one product. So again, just to finish up on the direct transfer switch charging solution, you're really looking at a lot less complexity with this solution. The nice thing is it takes up to, the switch is rated to 30 amps, so your max ISC according to NEC requirements can be 24 amps. It's really intended to support 2 input strings, which can be combined in an internal bus bar underneath the enclosure faceplate. And so everything has it, it's very tidy, tons of wiring room and nice layout, just how an installer would want it. You have the pass-through with the connection to the grid-tied inverter terminals right there under the faceplate as well. Everything all in one box just makes for a tidy install. And so, again, we'll talk about a few additional aspects of this. As you can see here, this lays out the components of the total solution. So in addition to our component, which again would be the charge controller with the transfer switch, the optional GFPD, you're going to need batteries, obviously. You're going to need a battery-based inverter charger. The nice thing is these are pretty much, manufacturer agnostic components. We can work with anything because, again, they're independent of the rest of the system operation. So we'll tell you about different criteria you should use to evaluate those other components as well. With the inverter charger, again, you select it purely based on the power rating. Your system voltage is going to depend on your battery specifications and your backup requirements. So again, just a very flexible solution with predictable guidelines for how to size these things without having to oversize, beyond any shadow of a doubt, where you're worried about not having enough power to make it through. You're going to realize that you're making a lot more of the power that you are able to harvest because it's being preserved more efficiently. Again, the AC transfer switch, most times you don't have to worry about that. It's built in. You can get, an external, most are automatic these days, but you could do manual. And then, basically just choose your manufacturer. It's nice to have that flexibility. Same with the sub panel. You're just, connecting power to your critical loads. You can, again, add or subtract loads as needed. During an outage, it's pretty easy to do on the fly, as your definition of critical loads may change over time. And again, the proximity to the wiring location will affect the cost as well. So all of these things need to be considered from a design standpoint. Anyway, that just outlines some of the components for a reliable grid-tied retrofit solution to add storage. One of the things that we can speak confidently about is MorningStar really knows how to charge batteries. We've been doing that for 26 years, almost 27 years now, actually. And, we have a broad portfolio of charge controllers, both in the PWM and the MPPT categories. We'll talk about those in just a second. But just to back up a little bit, to give a little more concept of how we fit into the system and why you're best suited to select a component from MorningStar. Again, being mostly responsible for the charge controller components, we're regulating power to the battery, allow it to maintain a high state of charge without overcharging. It's very important to keep a tight control loop on that voltage and current you're sending to the battery. And it, in some cases, needs to regulate the voltage from the PV panels as well. A lot of additional brains inside the controller with, self-diagnostics, to alert you of different things going on in the system that the user or operator should be aware of. A lot of, sophisticated programmability for different battery types, system monitoring for remote communications, all kinds of stuff really sits within the charge controller centralized brains to oversee everything. And then, of course, as you're powering AC loads, we have, inverters as well. And for MorningStar right now, we just have a small 12-volt inverter for 300-watt power systems. We are planning to expand that in the very near future, so we'll keep you updated on that as well. And again, sort of a contrast to the AC load example. In many cases, especially with our components, they may be used in more industrial applications that just have DC loads, DC load operation. And so many times you'll find that the charge controller has everything you need included in one component to manage both the loads and the battery charging. Many of our charge controllers have an integrated load circuit for load management. You can use it for lighting control to turn loads on and off at different times of the day in a scheduled manner, and prevent high voltage spikes for damaging loads, and all kinds of additional functionality built into that side of the component as well. This just gives you an overview of our all of the charge controllers that we offer that are compatible with lithium batteries, as that's a common request we get. You have the two PWM charge controllers over here that are custom programmable for lithium, and then our whole range of MPPTs is also custom programmable for lithium. Here is the 600-volt unit that we were talking about before in the earlier example. And then just quickly to wrap this up before I hand it back over to Troy, just wanted to talk about the two different types of charge controllers, because that is something that consumers will often have to decide on whether they're better suited to MPPT or PWM. MPPT stands for maximum power point tracking, and PWM stands for pulse width modulation. The MPPTs you'll see a lot these days, mainly for their capability to work with higher voltage arrays. So again, with a 600 volt array, very often you're going to be using an MPPT charge controller. You're going to need the sophistication of the buck topology, as it's called, which is a step down DC to DC voltage conversion to charge the more common off-grid nominal battery voltages at 12, 24, 48 volts, but still being able to accommodate the higher voltage solar arrays that you might find on rooftops without having to rewire everything, as we talked about earlier. MPPTs are really typically going to have the most benefit in colder climates. The cold temperatures cause the array to go closer to their open circuit voltages in accordance with their temperature coefficient as stated on the module data sheets. So as that happens, that creates a larger voltage barrier between the array and the battery, and you need to have an efficient conversion process to basically step down the voltage, but actually boost the current on the output so power is preserved. This basically just illustrates the MPPT technology. Again, each of the solar panels has a maximum power point represented by VMP, the maximum power voltage, and IMP, the maximum power current. And you can see that right on the knee of the IV curve here, I standing for current, V for voltage. This is where you want to operate the array in order to maximize its output. However, PWM controllers typically can only operate based on whatever the battery voltage range is. So if the battery voltage fluctuates, it's a 12 volt battery, you're going to get swings from 10 to 15 volts depending on state of charge. You're only able to harvest this amount of power under the curve, and you're losing a lot of this additional power that could be harvested if you were able to step up the voltage, step down the voltage and increase the current. And that's really what the MPPT controllers do. All right, and the PWMs, just to wrap it up, the PWMs, again, only operate at battery voltage. So you have to make sure that your array is sized in accordance with your nominal system voltage. So if it's a 48 volt battery system, you have to have a nominal 48 volt array, which would typically mean 2 72 cell modules in series. Similarly, for a 24 volt system, you may have one 72 cell module per string with maybe parallel strings. You could have 2 12 volt or 36 cell modules in series to equate to that 24 volt system voltage. Those are the types of constraints that are prevalent with the PWM controllers that you are not necessarily subject to with the MPPTs. So you just want to be aware of those differences. All of it will equate to, a longer battery life. You're going to have more reserve power and greater solar harvesting efficiency. So all of those things you want to, weigh heavily on your decision in choosing the proper technology to construct your system. And with that, I will hand it over to Troy.
Awesome. Thank you, Jake. I'm going to just go ahead and see here. Oh, sorry, everyone. A little hard to take control back. Okay. Awesome. Well, I just want to talk a little bit about batteries, what SimpliPhi does. I won't go too in depth. I think really what we're trying to highlight here is more about kind of the stuff Jake's talking about and really the parts and pieces, which he covered great. So we'll just briefly talk about batteries. I see a ton of questions, just FYI, so we will start digging through those here once these slides are all wrapped up. So basically, you know, looking at the lithium battery as a whole, why does it make sense to go with the lithium battery when it comes to you know, backup system, and specifically LFP, lithium iron phosphate? Well, the good news is with the lithium iron phosphate chemistry, we can have a greater depth of discharge while really not giving away too much cycle life. So we really maintain that longevity in the battery while also being able to discharge greatly, which in a backup situation can really be helpful to use, you know, that 100% of the battery's capacity if needed. Also, and I'll get into this coming up here in a few slides, but really the power capacity too, which makes a big difference. The ability to use a smaller battery bank, loads, and even surge that might come up in a household during a backup situation. Okay, so just a little bit about the company. I'd be remiss if I didn't mention kind of where we're at. This is kind of where we're at as far as, you know, systems landed, installed, 100+ megawatt hours. It's about 2010. You know, you can see here we're reaching out globally. Definitely, you know, biggest market still in the United States, but growing ever since in other markets as well. What we do is non-cobalt based chemistry, so lithium chemistry that is lithium iron phosphate. It's safe. It has no chance of or no risk of thermal runaway. UL certified batteries, proven technologies. Again, you know, with 100 megawatt hours installed in over 40 countries, and even validated through the U.S. Army and Marine Corps, and really try to strive for simple solutions, which I think really ties into what Jake's talking about with, you know, really simple, you know, making your install as simple as possible, covering the loads you need to cover, and picking the right solution. So again, lithium iron phosphate is chemistry we choose to go with. You can see here some other lithium type chemistries like NMC, which you're all probably familiar with if you use, you know, things like the Powerwall or the LG Chem. But we try to stick with lithium iron phosphate, or we do stick with lithium iron phosphate. There's no chance of thermal runaway. It's non-toxic. It can actually be recycled very easily, and it can withstand some pretty high temperatures due to not needing cooling or anything like that. So a lot of redundancies are taken out when using LFP, and you really kind of see a lot more safety and performance out of the battery. So again, lithium iron phosphate chemistry to build SimpliPhi batteries using a cylindrical form factor. This is just the form factor that we use building out these batteries. We've tried, you know, all other types of form factors and even other types of chemistries in the beginning. And really we're finding that lithium iron phosphate with cylindrical form factor gives us the best performance, lifespan, and safety out of the battery. So some kind of key features: scalability and expandability. You know, these scalability maybe not super relevant to what we're talking about today. The ability to build out, you know, parallel a lot of batteries. You know, this system on the left here, 88 batteries in parallel, 300 kilowatt hours. But we do have that ability to scale up these batteries in parallel. You know, whether it's our 12, 24, or 48 volt battery. Probably more relevant to this presentation is expansion. We actually allow for new batteries to be placed on old battery systems, so you can actually expand that system. So this could be super helpful if you're an installer. Maybe you put in a system, a customer doesn't really convey their critical loads properly in the backup system. You can actually go back and add batteries, so you're not stifled to having just whatever you size in the beginning. You can fix it up and add more storage. And that might even just be that the customer's needs grow. And I would say probably the most important factor when it comes to backup, power rating. And we'll talk kind of briefly about that, and I'll go into it again on, I believe, the next slide. But as far as power rating goes, you know, when it comes to lithium iron phosphate batteries, we rate it a C/2. So this means, you know, we also have the battery's capacity rated at that fast discharge, but also that the battery can discharge continuously at a 2-hour rate. So this can definitely help if you only need a little bit of backup to cover a lot of loads. You can have a relatively small battery bank. We also rate for instance, our 48 volt, 3.8 kilowatt hour battery, that black box you've seen, is actually rated at 60 amps DC for 10 minutes. What does this mean for a backup system? It means we can cover some pretty heavy loads like well pumps, some startup loads, things like that, with a relatively small battery bank. This can be super helpful when it comes to backup systems. And beyond even the C/2 rate, just understanding the maximum power that you can get out of these batteries. So we'll just talk briefly about just application-wise. Residential off-grid still, while not specifically backup, we're talking large off-grid, small off-grid, but DC-coupled systems, why does this battery make sense? Long, reliable lifespan. Again, the C/2 and the surge for greater demands. Small footprint, definitely if we're comparing to lead acid, the power and the footprint and the energy, actual storage per size of the battery, this is going to have the smallest footprint. Low self-discharge, which I'll talk about how that affects backup systems as well. No thermal runaway. I think this is crucial for all systems, whether it's off-grid, on-grid. Maybe it doesn't even tie to renewables. Maybe it's, who knows what it is, but it is so crucial to have no thermal runaway, as if this is in a home, to really protect the home safety. And warranted for off-grid, so there's no required monitoring or anything like that. Now to what we've been talking about, why does the SimpliPhi battery really make sense in a grid-tied battery backup system? Well, we're talking about DC-coupled systems. This is what I would almost call a hybrid system, and really what Jake's talking about with the MorningStar 600-volt charge controller, a dynamic DC charging, greater efficiency that way, still maintaining the functions like cell, time of use, backup, using that battery for multiple functions, while also being able to hold that storage for when you need it, when the grid goes down. We can seamlessly charge when the grid is down, when it's DC coupled, and the ability to actually tie more PV to a system with the idea that we're limiting the charger. And we'll go into kind of some examples with the MorningStar specifically. And of course, longevity and reliability with the battery. Excuse me. And just one more kind of note, diesel offset. We've talked about generators. Why does it make sense to have a battery in place of a diesel generator? Or even more to the effect, how can we add a battery and a controller and an inverter and a PV array and still have a generator on site? Well, we can cut our diesel by 50 to 70% offset just by adding storage in. You add PV, you're getting even more now. You can even offset that greater. But really, as far as ROI and looking at it over time, and as Jake mentioned with maintenance and things like that, it does actually save costs in the end. Okay, so let's say we are sizing, based on critical loads for a customer, and we're looking at, what a customer might have as far as wants for backup. This is just an example. You're pulling your loads here, your quantity of that load, the power rating of that load, and how long it operates per day. So if you have a refrigerator, it typically will, on the specifications, tell you, what's the actual runtime at that 180 watts. From there, we get our energy consumption per day, and we can add all of our loads together. So in this specific case, we can see that we have about 6.6 kilowatt hours, or 6,634 watt hours of storage that we're looking to cover. So to the effect of what Jake's talking about, and looking at the MorningStar 600-volt charge controller solution kind of versus AC coupling, this is really where we break down and you'll kind of get an understanding. I'll have some slides after this regarding battery sizing. I think that'll pull this all together. But, when we're AC coupling, let's say we have a 6 kilowatt string inverter, or let's just even say array. And basically now we're tied to that 6 kilowatts plus probably a 1.25 adder. And that's really what we need to base our multi-mode battery battery-based inverter size off of. So in that case, we would need a minimum. Let's say our inverter is a 4.4 kilowatt inverter charger. This is a battery-based charger. We would need 2 of those actually. Now, per SimpliPhi's guidelines, we actually require that you have double the output. So let's say you have 4,000 watts of output, or in this case, let's say you have 8,000 watts of output out of your multi-mode inverter charger. You would actually need 16 kilowatt hours battery. So regardless, in this case, of what the customer is asking for to go back, 6.6 kilowatt hours, just due to the array size in this case, we had to add 2 inverters, battery-based inverters, and to match that output, per SimpliPhi guidelines, we needed 6 batteries. So this comes out, about $25,000, and why it's a great system, and it does cover, a lot of loads. It might not be what the customer is looking for. Maybe their budget isn't allowing them to go that way. With the MorningStar DC Direct transfer switch solution, we actually have the ability to choose kind of how much PV, even when the controller's with full power here, we would only need 3 batteries in this case. We only need 1 inverter, and the cost actually comes out as lower. So we don't need to worry so much about the array size, as we can limit the array as far as what it pushes into the battery. And that'll make more sense here, I think, on the next example that you'll really see. So this example is even smaller. And, frankly, I get these questions all the time. I get people calling saying, I really just want to back up, 2,000 watts of load over a day. And that's all they're looking to cover. And that's pretty common, actually, that people are looking to cover very small loads. But to go back, oftentimes they are caught up into this, existing array, causing them to have a fairly large system that they did not really want. So this example is even, I think, makes even more sense. So, again, the 6 kilowatt array. So again, 2 inverters with the AC coupling. That's just per the battery-based inverter's requirements of how much you need to be able to AC couple that array into that multi-mode inverter. And then per those 2 inverters, now we need 6 batteries to cover the output of the inverter into the critical loads panel. And on the other hand, we know that the loads are minimal, so we only go with the 1 3.6 kilowatt inverter charger. Now, we only need 2 batteries in that case to cover the output, and we've saved a ton of money. So you can actually see here in this specific example, we're talking about the controller being set to 30 amps. So again, we're limiting that charge. In an AC coupled situation, even regardless of the multi-mode inverters requirements, we require a minimum of C/2. Frequency shifting, AC coupling, it's not foolproof, and we can't necessarily rely on the limitations set in those systems to work. Whether they do or not, there's just too much that's gone wrong that we just try to, we have to follow certain guidelines. In this case, we can rely on that 30 amp limitation put out by the 600 volt charge controller. So you can see the cost difference here is great, $13,000, almost $14,000. And the customer really is able to back up only what they wanted and to limit their cost based on that. So again, most of what that's based on is how the PV, and I know that's kind of a confusing idea, but if you've done AC coupled systems, you probably understand the concept. And it's really based on, what that battery-based inverter wants to see as far as how many inverters you need, or what its limit is as far as PV in on the AC coupled array. as well as our output limitation, which is basically understanding that we require C/2 guidelines. The battery should be sized to twice the inverter's output capacity. Now, again, you have to add more inverters just to cover the array, and then you have to in turn add more batteries. Whereas when we go with the DC coupled solution, the DC direct transfer switch solution, we are able to go with a smaller battery-based inverter. As we're not AC coupling that array, we are choosing how much of that array we really want to be charging those batteries as well. So just some other, like 2 more slides here, just quick notes on battery sizing. Depth of discharge again. This has actually changed. So very, very, very recently, we warranty 10 years for all depths of discharge now. But as far as longevity goes, these cycle lives are probably fairly realistic. So we want to look at, if you are in a backup situation and you don't use the battery very often, you can discharge a little bit lower. And of course, 80% is ideal, but 100% is not going to hurt the battery if it's only a backup situation. Again, so backup, you can use 90, 100%. If you are off grid, just a quick note, you probably want to use 80%. But again, you've got some wiggle room on that depth of discharge. So I believe that was the last slide. Perfect. We've got, let's take a look, a lot of questions here. I will do my very best to get through as many as we possibly can. And if your question does not get answered, we'll try to follow up after the fact. Okay, so let's go ahead and pop these open. How is the inventory situation with SimpliPhi? Lead times seem long from past experience. Yeah, no lying here. I mean, through COVID-19 and we did have to shut down very briefly. We did, we're seeing a greater demand, first of all, but we had a bit of a slowdown. We're just about back on track. So those lead times are going to be right back to where they should be very soon. But yeah, it was a bit of a slowdown. And even through some of our distribution partners who had to shut down as well, it's been a bit of a game to learn how to kind of work in this world. Okay, this one's for you, Jake. Jake, please explain the importance of battery cable lengths. I'm not actually sure if that's specifically for you, but it says Jake.
Well, that's a good one. I guess the main thing that we always caution about is, the voltage drop, and, having balancing issues with sort of uneven charging or uneven charge distribution through battery banks. I think you guys, SimpliPhi, always recommend parallel wiring to a bus bar. Is that right, Troy?
That's correct.
So that you can have you can guarantee equal length parallel connections or equal length inter-battery cabling to the bus bar to make sure that, again, the battery charge is evenly distributed. You don't get any balancing issues with certain areas of the bank getting charged more than others. The voltage drop is usually the one that, we see the most in terms of bad installation errors where, you're daisy chaining in between, which they don't recommend you do for SimpliPhi batteries, and then they'll just take the home runs on either opposite sides of the bank, but you'll get a lot of unequal length cabling based on just distance from, the mounting location. And that's where, again, you'll see there are some benefits for MorningStar where, just trying to get more accurate voltage measurements, separate from the inter-battery cabling, but just battery measurements for, battery voltage as perceived by the charge controller. They're very accurate measurements directly on the terminal input connections on the controller, but they can be even more accurate measuring the voltage directly on the battery terminals themselves, and then having the charge controller have that reference, they can compensate for any voltage drop over a certain amount of distance. So we always recommend using the optional voltage sense wiring available on many of our controllers to get better quality and more accurate charging regulation. Hope that answered the question.
No, absolutely. And just to add to that, battery cables, while also be affected as far as the length for charging and that even distribution, we also need to think output as well. So discharging, again, and too long of cables or mismatched cables, I think that's the biggest issue I would see is improper lengths that are not the same. That's where you're going to see issues.
We also
will this be? Oh, go ahead. No, go.
Oh, sorry, Troy. I just wanted to mention we also put some wire sizing guidelines, charts, reference charts at the end of our product manuals for the battery connections, to the charge controller. So if you're trying to figure out what gauge wire based on a certain distance away from the controller, those tools can be handy as well. Just thought I'd mention that.
Awesome. Yeah. And actually we have a wire sizing guide as well for the battery side. So check out both of them. It'll be perfect. Okay, will this be recorded and will be able to shareable? So we did record today. We'll send out the PDF probably sometime either today or tomorrow. Recording probably won't be live until sometimes next week, but you'll see a follow-up and you'll be able to watch the video. Okay, the DC coupled block diagram showed all solar energy flowing through the battery. I assume this is a simplification of the diagram, and the solar energy serving real-time loads is not unnecessarily exercising the battery. Can you please clarify?
Right, that's a good question as well. So I'm just trying to visualize which diagram you were referencing specifically, but I think, again, for the DC coupled, that would have the charge controller regulating DC to DC conversion to charge the battery. And there is the ability to dial back the current, through a programmed current limitation based on, not wanting to exceed specific battery's maximum charging current recommendation. So you can do that. The charge controller, because the load is connected, the load would be traditionally on the AC side through the inverter for these, residential type systems. The charge controller is not regulating the load. Therefore, it's regulating purely based on what the battery needs. Now, the inverter can obviously be operating loads simultaneously, pulling power out of the battery as the charge controller is dumping current in, and they're all tied to, a common DC bus. So you won't see excessive cycling, but it's not going to be able to push power directly out to the load. Like if the battery is full and the solar array, you still have full sunshine, full potential power output, the charge controller will dial back based on what it sees at the output of the DC bus. So again, it's regulated by voltage. The voltages for SimpliPhi batteries are going to be very stable. So you could have loads running on the AC side, and the voltage will be pretty resilient. The charge controller is still going to limit current. If you want to harvest the additional power available from the solar array while the battery is already near the top or getting full, then you can put in, diversion dump loads for, resistive heating. If you want to do a hot water heater or something like that, that's always a good way to harvest to ensure you're harvesting, the maximum energy out of your array, and that the controller stays in MPPT and it doesn't dial back the current. So there are different ways of doing that, but yes, unless right now, because we don't control the load directly, we would be regulating purely based on the voltage on that common DC bus. So yep. Again, if it's at the top of the range there for what indicates a full battery state of charge, it will start to dial back the current, and you may be able to harvest more energy available. You just have to find another way to do that, either through diversion control or parallel systems.
Awesome.
Expanding your battery bank.
Question I see, I'll just go ahead and answer. Does the 600 volt charge controller work or charge 48 volt batteries? It does indeed. I can attest to that. It does charge, or else our presentation might have been for nothing here, but it does.
It can also do 24 volt and other awesome. Custom intermediate voltages. It would just be through custom programming. The one thing I always like to caution is that the 600 volt rating is really best suited to the 48 volt nominal battery system. If you're using it on a 24 volt system, you're not going to be able to stretch the array voltage quite as high before the controller will start to derate. So it's just a matter of, how wide the input tolerance is. So if you really want to achieve, if you're retrofitting a grid-tied system in a residential setting, you're talking about, a array that can be up to 600 volts, then you really want to use a 48 volt battery for your backup system if you're using that controller, because that's where you're going to have the highest ceiling in terms of voltage limitation. With 24 volt batteries, you'll probably only get, probably around 360 volts before it will start to limit the current or limit the power output of the controller.
Awesome. Okay, I see a question. Carbon batteries are being sold as competitive solutions for lithium batteries. Could you explain the main differences here between both technologies and the advantage of lithium ion? Yeah, absolutely. I mean, carbon batteries really are not that different than LAs here, looking at lead acids. I mean, we're still looking at lower lifespans. I don't know if I've seen, I guess I have not picked through warranties too much, but I can't imagine that they're warrantying anywhere close to 10,000 cycles or anything like that, or that we would even expect the lifespan to last that long. Power as well. Again, I've not picked through a spec sheet specifically, but I have a funny feeling that the carbon batteries are not suited for continuous C/2 rate or high surge capacity. So again, it's a bigger investment typically when it comes to lithium batteries, but you see a longer LCOE, levelized cost of energy, or ROI in the end. Okay, this question for you, Jake. I'm going to go ahead and just sum up two questions here. I think that we can kind of knock them both out at once. What grid-tied string inverter, or wait, sorry here. Basically asking, does this only work with a single PV inverter and not microinverters? And then the second part of that is, can you speak to how it works with, specifically asking about the solar edge optimizers, but we can generalize that, I think, into how does this solution work with all optimizers?
Those are both good questions. So yes, the transfer switch solution does require, a centralized string inverter. So it can't be producing AC directly on the panels like with microinverters. So our solution would not be compatible with microinverters. With optimizers, you can use TIGO optimizers. They have been used successfully with our products in the past. Those are different than Solar Edge. Solar Edge, I think they have a keep alive signal with their string inverter. So if communication is interrupted when you change over to backup mode, it would interrupt the communications, breaking that link, and basically it isolates itself. So SolarEdge keeps everything, proprietary, internal with their communication protocol. So their optimizers can only talk to their string inverters, and they have to preserve that communication. So that wouldn't work for our solution. But Tigo, because they're not really tied down to any one particular string inverter, they can actually plug in directly to a 45 connection on our controller, and they can monitor it through their cloud portal. We've tested that and done so successfully with their optimizers. Our MPPTs can actually operate at a fixed input voltage if you specify that as the setting in your custom programming. So you can just fix the input voltage on the charge controller to be whatever the output of the DC optimizers are, so that it will disable the sweeping. It will allow the optimizers to basically sweep on a module level versus sweeping the whole array with the controller, and that works well. So just depends. I know a lot of times the code benefits, or there may be some advantages to using the module level components for rapid shutdown and that kind of stuff, and module level monitoring for troubleshooting different issues that may occur within your array, being able to pinpoint those troublesome modules. Those are good reasons to use them. And yes, you can use the Tigo optimizers, just not the SolarEdge.
Awesome. I see a temperature here regarding cold temperature limitations, both for charging and discharging. So basically, there are two different ones here when we're looking at this. I really would not recommend looking too much at the discharge limitation. It is lower. We can actually go to 0 degrees Fahrenheit on the discharge, but really, most of the time we're looking at the charging as what's the temperature limitation, and that would be 32 degrees Fahrenheit to 0 degrees Celsius. High end is 49 degrees Celsius or 120 degrees Fahrenheit. We do, however, I do want to mention, we're implementing cold weather applications with our, basically it's a hot start that can be added to the batteries that can act as basically an internal heater. And this is ready to be implemented now and go out for cold weather applications where we can keep the battery's internal temperature above those limits in a cold weather application. Great. Good question. What is the main difference between lithium iron phosphate and lithium ferrous phosphate? There is no difference. Iron, ferrous, same thing. So same battery. Jake, what is the max output on the battery side for the 600 volt MPPT? I'm guessing
so it's 60 amps of maximum charging current. And again, compatible with 24 volt batteries through custom programming, but again, most best nominally configured for 48 volt batteries. It can harvest a nominal power rating of 3,200 watts at the 60 amps.
Perfect. All right. And I just want to tell everybody, we have still about 80 questions, and I believe we have about 15 minutes left. So I do apologize. We're not going to be able to get to everyone's questions, but we'll do our best to keep pushing through these. Jake, not to put you on the spot here, when is your new inverter going to be available?
Oh man, you had to ask. So I don't have a specific launch date yet. Again, it is, I hear frequently from our engineering team, we're making great progress. And I think even despite the whole coronavirus outbreak, we've been able to maintain pace. So I'm personally hoping it would be a great end of the year gift. I'm not going to commit to anything because I know better than that.
Me too. I do the same with ours. So, okay, here's a question. In daily usage, does the battery support the load in the evening? That's up to you, really, especially when we're talking about these hybrid systems. So, I've got tons of customers that do have, even with this design, again, you've got your battery-based inverter that does have that function to say, when to discharge typically. And just a quick note, when AC coupling, I know of 0 inverters that can do true time of use. When it comes to AC coupled systems, there's no such thing as true time of use from what maybe somebody can school me on this, but I've never once seen it. I can use the grid timers, grid use timers, but no true time of use. The benefits of being DC coupled is that we truly can use that time of use function on these inverters and cover those TOU demands. But again, as far as how you want your battery to discharge, that's really up to you, and that's programmable to say, I do want to cover certain loads or even sell off the battery in certain cases. Okay, so Jake, I see a lot of questions coming in on this one. Can you just kind of speak to the need of the customer to actually operate the DC transfer switch?
Sure. Yeah, so it is a manual transfer switch. Again, if we go back to the diagram we were looking at before, with all the components in the single line diagram, we had the AC transfer switch built into the battery-based inverter. That is automatic. So again, that just detects the presence of AC. As soon as that drops out, it changes from a charger to an inverter basically, and will back up the critical loads in the subpanel. That will happen instantaneously. Many of them, again, are flicker free in terms of their response time. They qualify as a UPS, uninterruptible power supply. So but again, however you size your battery, this is just a pure grid backup scenario where you just want to buy, 8 hours of runtime in the case of an outage. Then you just have to remember to go out and turn the switch. When you turn the switch, you're going to start charging again, right? So your loads are going to pick up automatically as soon as the grid goes down, and then you have the full autonomy of the battery in terms of your runtime to be able to go out and turn the switch. When you turn the switch, you'll be able to start charging again using your PV array to charge back up the battery. And then when the utility comes back online, you're going to hopefully remember to go turn it back so that, again, you can utilize the high efficiency of the grid cell operation through the string inverter when you're doing that. So yes, it is manual operation for both ways. But again, the loads on the AC side will be carried over through the automatic AC transfer switch. It just then depends on how your battery is sized in terms of how much runtime or autonomy you can have for your system to be unattended, basically.
Awesome. Question about availability in recycling. I'm guessing this is pointing towards the batteries. We can always help you. We don't recycle direct, but typically we can either accommodate or help direct you as far as recycling batteries go. Depending on your region, they might need to be shipped somewhere, but we definitely have a key eye on who does and who doesn't and where to go for that. Okay, let's see. Okay, I see a question. What about module level rapid shutdown? I'll try to take a stab at this, and Jake, let me know if I missed anything. But, in this situation, Jake mentioned the Tigos earlier for optimizers. Tigo and Midnight as well, you still have those solutions available that are just rapid shutdown. components. Basically, they look like microinverters, but they just clip to panels to get that module level rapid shutdown compliance, even in a DC coupled situation. Anything you want to add there, Jake?
Yeah, I can. So the code compliance, again, is obviously going to vary based on your region. The two requirements, that may be needed, mostly if, it really depends how your local code defines a retrofit. So if you have to have the system re-inspected because it's considered, new electrical work, then yes, you will have to have all of the up-to-date code requirements for your specific location. If it's not being re-inspected and it's just, considered, an extension of your existing system, then maybe you don't, then you don't have to. It could possibly be grandfathered in with the old rules when the system was first put into place, essentially. Again, you're going to want to check with your local inspector or, authority having jurisdiction and all of that. But as far as the code compliance for rapid shutdown, we do know that there is a solution from IMO, actually. They're a British company that makes the module level rapid shutdown solution, NEC 2019 compliant. It just operates with a disconnect at the controller, so it doesn't need the power line communication like some of the other types. I think Midnight uses power line, and Tigo has both wireless and they have a wireless integration with their safety module that can be combined with their optimizers. And then they also have a PLC, power line communication variant. We wouldn't be compatible with any of the power line communication variants because we don't have the PLC transmitter built in. No way to interpret that, but the pure just disconnect at the controller or the wireless safety optimizer from Tigo would both be compatible. The one from IMO I tend to recommend most highly just because with our experience, that's the one we've tested and can speak more confidently to. With the arc fault requirements that typically go along with, if rapid shutdown is required, typically arc fault is required as well. The arc fault solution, we do not have anything built in internally. So you would have to source a third-party arc fault detection unit. There are, many of them out there. However, I can't guarantee that they will work because many of them need to be calibrated specifically for each manufacturer's device based on its MPPT tracking behavior, how often it sweeps and that kind of thing. So I can't guarantee or recommend any specific solution, but you would have to source a third party for that. But with rapid shutdown, IMO, I can confidently say does work with our solution.
Awesome. Okay, let's see here. Probably got time for maybe one or two more here. Why do you recommend the battery bank to be sized to twice the inverter's capacity? Is this a requirement of all battery types or just SimpliPhi? I can't speak if it's a requirement of all battery types. I would say it's probably a requirement of a lot of batteries. Basically looking at, the inverter's output does not have a way to be limited in most cases. Even the ones that do have a way to be limited tend to only have a way to be limited when the grid is present or maybe a generator is present and there's some sort of AC support. So, when it comes to the battery, we're just trying to protect the battery's performance. Its maximum continuous discharge is C/2. So if you have, an 8,000 watt inverter and you only have two batteries, let's say, chances are you put that 8,000 watt inverter in there because there are extremely high loads. And if you don't need that big of an inverter, I would just recommend going with a smaller inverter. But oftentimes, we see with a big inverter and a small battery bank, the battery will be pushed beyond its continuous discharge limit multiple times until the battery does encounter damage. This is where that C/2 recommendation comes from. Now, C/2 related to AC coupling specifically, with frequency shifting and even other mechanisms of AC coupling, we tend to assume that it's always going to be flawless and that your 6,000 watt array will be limited to 5,000 watts or whatever the limit is. And this just isn't always the case. There are, when it comes to compatibility between the battery-based inverter, the grid-tied inverters, what model they are, what UL rating they have, what their frequency range is, oftentimes there's a high chance that you might see that entire PV array, even with a limit set, try to charge the battery. And that's really where that C/2 limit also comes into play as far as sizing an AC coupled array.
Yeah, especially with the the cloud edge effect and that kind of thing too, can have a big, in terms of like the oversizing capability of the string inverters, they may only be like 125% of their nominal rating. And so again, you have to be able to take all of that output and dump it somewhere. And a lot of the frequency shift, even with cloud edge effect, you get spikes on the array that cause, current jumps that needs to go somewhere as well. And so, yeah, I think generally that's where they get that oversizing factor from, to make sure that you can withstand not only the full output capacity, but even more so with surge.
Yep, agreed. Okay, so I think we're just about out of time. I'm going to go ahead and answer just one more question. I'm curious. I saw a question come in that says, when will the NAPCEP credits be sent? As far as my end, not NAPCEP approved this training. Jake, the same for you, is correct? No CEUs.
I assume so, but I'll have to check. I'll follow up with our marketing to see if that is indeed the case.
Yep. Okay. Well, hey, everyone, there's still a good 60 plus questions. We might be here all day trying to answer them, but we will do our best to go back through the questions, see if we can send some follow-ups. Feel free to respond to the follow-up with the PDF with questions. And again, that can be, we'll try to coordinate here where the follow-up can go out to both Morningstar and SimpliPhi. And we can try to, if you've got a question for either one of us, go ahead and respond back. And again, the recording of this presentation, we will try to make live here as soon as we can, and be able to share that with everybody. But Jake, I really appreciate your time. Big thanks to Morningstar for putting a lot of this together. And great presentation, and thanks everyone else for joining.
Same to you, Troy. Appreciate everybody joining. Thanks.
Thank you.